Welcome back. So in the last class, we have discussed about time domain relay line cancellers. So the main problem which we encountered in time domain relay line cancellers is the blind speed. Okay. So the blind speeds are nothing but the velocities at which the radar is unable to detect the desired signal, which is nothing but the echo signal coming from the moving targets. Okay, and we had seen that so whenever the Doppler frequency is equal to the pulse distribution frequency, the frequency response of the received echo signal is going to be 0. So these are the disadvantages of time domain delay line cancellers. So these can be eliminated if we can select more than one pulse repetition frequency. So which is nothing but the usage of multiple pulse repetitive frequencies. Okay, the use of more than one pulse repetition frequency offers additional flexibility in the design of MPI Doppler filters. So if we use more than one pulse repetition frequency, so there is no chance of giving the false alarm. Okay, so whenever the Doppler frequency shifted signal frequency is equal to the pulse repetition frequency also, since here we are using multiple frequencies, there is no equality. Okay, so there is no similarity between Doppler shifted frequency signal, okay, so which is coming from the moving target, and the signals which we have transmitted from the transmitter. So it not only reduces the effect of the blind speeds, but it also allows a sharper low frequency cutoff in the frequency response than might be obtained with a cascade of single delay line cancellers. So with the use of multiple frequencies, so we not only can reduce the blind speeds, okay, because there is no similarity between F0 and FD. So that is why here there is no chance of blind speeds. Okay, but it also allows a sharper low frequency cutoff. That means when we apply different kinds of band pass filters such that it can reject the spectrum and can allow the signals which are coming from the moving targets. Okay, so these filters can offer a sharper low frequency cutoff. Okay, such that though the frequency is very less, okay, the frequency of Doppler shifted frequency, though the frequency of Doppler shifted signals is very less, so these filters can offer the cutoff necessary to allow such kind of signals by suppressing the flutters. So the pulse repetition frequency might be switched every other scan or every time the antenna is scanned a half beamwidth, or the period might be alternated on every other pulse. So here what we are going to do is, so we are going to transmit the pulses from the transmitter which are having multiple pulse repetition frequencies. Okay, so every time a radar transmits the pulse, so it has different pulse repetition frequencies. So whenever the antenna from transmitter is sending different types of pulses, okay, so when we select multiple pulse repetitive frequencies, okay, so the radar is able to recognize these kind of multiple repetitive frequencies while receiving echo signal, because so these frequencies are well known, understood by the radar, and it can separate that transmitted frequency signals. So when in case of receiving the received echo signal at the receiver. So whenever the antenna is scanned for the echo signals, okay, so which are coming from the moving targets, okay, so here the radar is able to recognize the separate, okay, the difference between the received echo signals which are coming from the moving targets and the pulses, okay, so which are coming from the stationary targets. So when switching is pulse to pulse, so whenever this frequency is varied from pulse to pulse, so that kind of phenomenon is known as staggered PRF, staggered pulse repetitive frequency. So here, this is the frequency response obtained in case of staggered pulse repetitive frequency. So if you observe here frequency versus the relative amplitudes of the received echo signal, okay. So here we can see there is no zero, okay. So whenever since we have applied multiple staggered pulse repetitive frequencies, so the frequency response is not zero, okay. So and then it can allow a lower cutoff frequency. It can allow the frequencies which are low enough, okay, and to be detected by the radars, so that the frequency response can be improved if we use staggered pulse repetitive frequencies. So this concept is well developed in range-gated Doppler filters. So here the use of multiple repetitive pulse frequencies and range-gated Doppler filters not only reduce the blind speeds, but also they can give the much improvised frequency response by allowing low cutoff frequency by using threshold filters, okay, and they can detect the frequency signals, okay, which are coming from the moving targets, okay. So though they have less frequency compared to the fixed targets, so the radar is able to detect the moving targets. So here the delay line canceller, which can be considered as a time domain filter, is widely used in anti-radar to separate moving targets from stationary clutter. So this we discussed already, okay. So delay line canceller is used to just provide a time delay, okay, and after that mostly it is used in case of time domain, okay. So it is used in the domain of time, okay. So whereas here range-gated Doppler filters are used in the domain of frequency, and mostly these are helpful to reduce the blind space and to recognize the echo signals which are coming from the moving targets. So it is possible to employ more common frequency domain bandpass filters of conventional design in MPA radar to separate the Doppler frequency shifted signals. So not only delay line cancellers help us to separate clutters from moving targets, but in the frequency domain, the application of bandpass filters will give us the same result, which is nothing but by eliminating clutter and detecting the moving targets. So the loss of range information and collapsing loss may be eliminated by first quantizing the range into small intervals. This process is called range gating. So here, what is the loss of range information? As we have discussed earlier, so when we have chosen narrow bandpass filters, okay, so what is the problem with narrow bandpass filters? So they might have lost the information in case of less frequencies of received echo signals. So that is why the range information can be lost, okay. So that is why to avoid such range information loss, okay, so here we are going to quantize, okay, the range, that means time, into small intervals. So here the time period is mostly selected in such a way that it is equal to the pulse period, okay, or pulse width, okay. So this process is known as range gating. And collapsing loss in the sense, so when the Doppler shifted echo signal has less frequency, so then the radar cannot see the target clearly. So which is known as collapsing loss. So this also can be eliminated, okay, so by quantizing and stretching the signal, the received echo signal at the receiver. So the width of the range gates depends upon the range accuracy, but they are usually of the order of pulse width. So as I said now, so the width of range gates, okay, is completely dependent on the pulse width. So this is the block diagram of the video of an empty radar with multiple range gates followed by clutter rejection filters. So here, if we observe at the receiver, when the receiver antenna receives the Doppler shifted frequency signal, so it is fed to the phase detector. Okay, so phase detector, what is the work of phase detector? So it separates it separates the carrier frequency and the Doppler shifted frequency signal. So here we will receive the Doppler shifted frequency signal, which is nothing but the echo signal of our interest, which is coming from the moving targets. So it is fed to the different range gates. So the number of range gates is of our interest. So this is general block diagram. So here we have taken n range gates. Okay. So these range gates act like switches. Okay. So they allow they receive echo signal to pass through them at proper time. Okay. For example, if range gate 1 allows the signal for a particular time period T1. So at another particular time period T2, range gate 2 allows the signal. So in such a way, these range gates act like switches and allow and pass the receive echo signal to them. And here, after the quantization of received echo signal, so it is fed to the boxcar generator. So boxcar generator generally contains the clamping circuit, which contains a capacitor in it. Okay, that capacitor maintains the voltage, which is equal to the pulse width. Okay, so whenever boxcar generator holds the circuit, okay, so it is capable of stretching the received echo signal such that multiple frequencies, okay, which are nothing but the repetitive frequencies, okay, so which are nothing but the harmonics, can be eliminated by using the boxcar generator. And after sample and hold, okay, so this is given to the band pass filter. So band pass filter is a filter which we are talking about now. Okay, so here we are using n band pass Doppler filters. Okay, so the frequency range of this band pass Doppler filter is of desired signal spectrum, okay, such that it can eliminate the cluttered spectrum. So it has to allow the frequency range, okay, which is in the range of Doppler shifted frequency signal, and it is able to avoid the clutter spectrum. And after it is given to the full wave rectifier detector. So the main use of full wave linear detector, okay, is nothing but it will convert the bipolar video into unipolar video. And after that, low pass filtering is done, okay, so which is nothing but the construction of received echo signal, okay, and then after construction of received echo pulse signal, okay, so it is allowed to the threshold detector. So the main work of okay, the main function of threshold detector is to detect the signals, okay, so which are coming from the moving targets. So it is able, it sets the some threshold value which is minimum enough, okay, so minimum enough to pass through it. So the signals which are above the threshold are detected by the radar as moving targets. So the signals which are below the threshold are eliminated as clutter. And after this detection, so the received signal, okay, is passed through the ASST for the further data processing. So here, if you see, the output of the phase detector is sampled sequentially by the range gates. So as I said earlier, so range gates operate at different times and acts like a switches. So each range gate opens in sequence just long enough to sample the voltage of the video waveform corresponding to a different range interval in space. Okay, so if each range gate opens at certain interval of time. So the range gate acts as a switch or a gate switch which opens and closes at the proper time. So first range gate opens at time period T1, the another range gate at operates at another time period, and so on. So the output of the range gates is stretched in a circuit called the boxcar generator. So as I mentioned earlier, so this is the output, okay, which we will be getting after the echo signal is passed through the boxcar generator. So it just gives us a sample and hold value, okay, so which aids in the filtering and eliminating harmonics of the pulse repetitive frequency. So since we are using the multiple repetitive frequencies, okay, so those are all not necessary in the received echo signal. So that is why we have to eliminate the pulse repetitive frequencies by stretching the output waveform. Okay, so the boxcar generator clamps the video pulse amplitude each time it is received. So whenever it receives the new pulse, okay, so it just hold throughout that pulse wave, and whenever it receives a new pulse, okay, so it will start operating on another amplitude. So and it eliminates the pulse repetitive frequency and reduces its harmonics. Since it is holding, okay, since it is stretching the pulse width, okay, multiple frequencies are eliminated which are nothing but the harmonics. So the clutter rejection filter, which is nothing but a band pass filter, whose bandwidth depends on the extent of the expected clutter spectrum. So the band pass filter's pass band is designed in such a way that it has to reject the expected clutter spectrum from mobile targets. The purpose of the wave detector is to convert the bipolar video to unipolar video. And the output of the integrator is applied to a threshold detection circuit. Only those signals which cross the threshold are reported as targets. So certain amplitude, okay, certain amplitude is set in threshold detector such that the signals which cross the threshold value are generally considered as moving targets, and the signals which do not cross the threshold level are generally eliminated as clutters. So following the threshold detector, the outputs from each of the range channels must be properly combined for the display on PPI or ASST or for any other appropriate indicating or data processing device. So at the receiver, okay, at the end of the threshold detector, so all these waveforms, okay, all these signals are displayed on ASST to determine the range information. So this is the frequency response of characteristic of the range gated MPI. So here we see this is the frequency and this is the relative response. So this is the characteristic, okay, of band pass filter which we have used in range gated Doppler radar. So this pass band, okay, so is designed in such a way, okay, that it will eliminate the clutter spectrum and is able to pass the Doppler shifted frequency signals. And coming to the performance of the radar, so there are some parameters which we need to consider. So based on which the radar can be selected. So those are nothing but the MTI improvement factor, subcluster visibility, clutter visibility factor, and the improvement factor. So these are the parameters which tell us the quality of radar. So MTI improvement factor is nothing but the signal to clutter ratio at the output of MTI system divided by the signal to clutter ratio at the input. So whenever we take the ratio of signal to clutter ratio of an output by input, okay, so this average should be uniform over all the target radial velocities. So this value should not be fluctuated if the radar is very quality one. So next one is subclutter visibility. So the ratio by which the target echo power may be weaker than the coincident clutter echo power and still be detected with specified detection and false alarm probabilities. So sometimes what happens is the targets, okay, the target signal, okay, they have the echo power which is very much weaker than the clutter echo power. So though the clutter is very much high, the radar must be able to detect the specified targets and avoid false alarm probabilities, which are nothing but the echo signals, okay, coming from the clutters like seas, hills, okay, etc. Next, clutter visibility factor. So it is much more similar to that of subclutter visibility. Okay, so for clutter visibility factor, the signal to clutter ratio after cancellation or Doppler filtering that provides stated probabilities of detection and false alarm. So whenever we allow the Doppler shifted frequency signal, okay, to the delay line canceller or range gated Doppler filters, okay, so the radar must be able to detect the movable targets and it should avoid the clutter false alarm. And the improvement factor, so which is equal to the subclutter visibility times the clutter visibility factor. So it is simply the ratio of subclutter visibility and the visibility factor. So in terms of decibels, it is expressed as IDB, okay, is equal to SCV, subclutter visibility in terms of dB, decibels, plus visibility, sorry, clutter visibility factor in terms of decibels. When MTI is limited by noise like system instabilities, the clutter visibility factor should be chosen as a signal to noise ratio as defined in Radar equation. So whenever the MTI has limitations like noise, okay, or if it is limited by the system instabilities, okay, so like the delay in propagation of delay line cancellers and system instabilities or any fluctuations in the oscillators. So in such cases, okay, so the clutter visibility factor should be chosen as the signal to noise ratio power. And till now we have discussed what are the parameters that we should learn, okay, to select any type of radar. So here we have some limitations for the any type of radar performance. So those are nothing but the equipment instabilities, internal fluctuation of clutter, and antenna scanning modulation. So these are the limitations to the any perfect radar. Okay. So though the radar is very quality radar, so we have to face some limitations. So the first one is equipment instabilities. So equipment instabilities include pulse to pulse changes in amplitude. Sometimes the transmitted pulses, okay, they may vary in their amplitude due to the interference of clusters, okay, and frequency of phase of the transmitted signal. So there may be change in frequency of phase, okay, of the transmitted signal. So if the coherence is missed, okay, So changes in the shallow or coho oscillators in the receiver. Okay, due to changes in shallow or coho oscillators coherence, so there may be frequency of phase shift is resulted in the transmitted signal. So variations in the time delay through the delay lines. So sometimes time delay, okay, band provided. So sometimes there can be a time delay offered by the delay lines due to the propagation. While propagation, they may undergo certain delay amount. So those can be a problem. And changes in the pulse width can cause the apparent frequency spectrum from perfectly stationary cluster to broaden and thereby lower the improvement factor of an MPI radar. Sometimes if there is change in pulse width, okay, so while we are clamping the output, okay, so the receiver echo signal. So if there is change in the pulse width, okay, there may be a chances of clutter interfere with the moving targets so that the clutter spectrum can be broadened, okay, which results in the reduction of the improvement factor of an MPI radar. And the internal fluctuations of clutter. So though there are some stationary targets, okay, whose amplitudes and frequencies are same and can be eliminated easily at the receiver. So there are some echoes, okay, which are from trees, vegetation, sea, wind, and they will fluctuate with time, okay. So these fluctuations can limit the performance of MPI radar. So because of its varied nature, since they vary from time to time, so it is difficult to describe precisely the clutter echo signal. So since their amplitudes, frequency, phase, okay, so they may be varied from time to time, okay, which is very unknown, okay. So sometimes it is very difficult to distinguish which is the clutter signal and which is the echo signal received from the moving targets. And the another one is antenna scanning modulation. So while antenna scans a target, it observes the target for a certain time interval, which is determined as T0 equal to NB by FT, which is also equal to theta B by theta bar S. So here NB is nothing but the number of hits it receives. Okay. So each time a pulse is transmitted, it receives every time that pulse. So here NB is the number of hits it receives, and FP is the pulse repetition frequency, and theta B is the antenna beamwidth, and theta bar S is the antenna scanning rate. Okay. So if the clutter spectrum is too wide, because the observation time is too short. So if the time is too short, then the clutter spectrum will become larger. So it will affect the improvement factor. So this limitation has sometimes been called scanning fluctuations or scanning modulation. So whenever the antenna scans a target, okay, so then it should observe the target for certain interval of time. So if the time is too short, the clusters may allow, okay, the clusters may pass through the antenna, so that this will cause the antenna improvement factor will get lesser. Hope you understand this concept. Thank you so much.